Quantitative information from balanced equations. This really is the meat of chemistry. It's about 80% of what professional chemists do. This is the methodology we use to figure out quantitatively how we can relate the reaction of one substance with another. We need to know how much of one substance reacts with a given amount of another. For example, how many tanker cars of this disgusting stuff must I order? And will they take that $10,000 out of my pay if I'm wrong? You also want to know which reactant will run out first, and mostly, will I get enough product? How much will it cost? Chemists don't do reactions for the fun of it very often. They want the product. Chemical equations are a very precise yet very versatile language that describes chemical changes. And we're going to learn a little bit about it right now. Okay, here's our combustion of methane. And you'll notice we've talked a little bit about before when we were balancing and in the first chapter about these coefficients in front of the species. They can be interpreted, they are numbers, and they can be interpreted as molecules for individuals. This is individual molecules. Okay, or we can multiply them by 6.02 times 10 to the 23rd. This is Avogadro's number. And this tells us how many particles are in a mole. So if we multiply times that number, we can convert into moles. And so the moles, not individuals, but collections of individuals. The reason, remember, we go to moles is because the mole quantities of atoms is in gram amounts, and we can easily weigh gram amounts. It is nearly impossible to to weigh one atom. All right. Okay, so the mole relationships between component molecules is called the mole ratio, or here's this fun word, stoichiometry. OHIO. That's anyway. All right. Well, we use stoichiometric ratios as conversion factors to relate one component to another. Okay, now I need you to think for a minute. We've talked about conversion factors before. We've talked about them in terms of unit conversions, one set of units to another, and this one's pretty straightforward for people. For example, 1 inch is equal to 2.54 centimeters. And people can pretty well understand that. But what I'm asking you to do is understand it in terms of relationships or equivalencies. So we've got two kinds of conversion factors. I hope I spelled that right. That's all right. And equivalencies are the same thing as saying, okay, for $1 you can get a cup of coffee. We can also write this as $1 equals cup of coffee. All right, now this equal sign means a little bit different. It means equivalence or related to, correlates with, linked to, associated with, all these different connotations. What we look at in a balanced equation is the stoichiometric ratios as conversion factors. So I say then that one CH4 unit, and it can be molecules or moles, or even formula units. We use the word formula unit for ionic compounds, but it's going to be one molecule or mole is stoichiometrically equivalent to 2 of the O2. And we just keep going to 1 of the CO2 and 2 of the waters. We can make ratios out of these and use these quantities, these relationships, in many, many different ways. Okay, for example, let's say we have 3.2 moles of methane and we want to know how many moles of oxygen we'll need to completely react this stuff. Let me get some of this out of the way and I'll write this down. Okay, we have 3.2 moles of CH4 and I want to know how many moles of oxygen I need to completely combust those 3.2 moles. We are going to use the conversion factor from the balanced equation. Well, I know it takes 2 moles of O2 to react with 1 mole of CH4. Here's 2 and 1. And then you double check to be sure that you've put these in the right, who's in the basement, who's in the attic. And there's 1 mole here. I'm sorry, there's moles methane there, moles methane here. And the whole purpose of using a conversion factor is convert from one quantity into a different quantity in different units. Okay, and the answer here would be 6.4. Okay, alrighty. How about this one? How many moles of each of the products will you get for this quantity of reactants? You could do it in your head, but let's do it together mathematically. Okay, so I have 3.2 moles of methane, and let's assume we've got 6.4 moles of O2. That means we're not limited by oxygen. How much of the carbon dioxide and the water would we produce? And again, let's just write our relationship. So this is a 1-to-1 mole relationship. And we'd have the same number for water here if we wanted to do as oxygen. So I could just take this out. You'll notice the coefficient for water is also 2. So let's just put here and here, and we are happy to say we get 6.2. 6.4. Great. We cannot convert directly from grams to moles. Come back here. The conservation of mass is upheld. On this side, has the same mass as this side, about 80 grams. And that's because you do have the same number and type of atom on each side of this little arrow. But you cannot go from grams to grams. You have to proceed through moles. Grams CH4 going to mole CH4 going to mole O2 and then grams O2. Alright, so this would be CH4 CH4 O2 O2. Lovely. Okay. We would take 24.0 grams CH4 times 16.04 grams is 1 mole CH4. Previous page, we saw from the balanced equation that 1 mole of CH4 relates stoichiometrically is equivalent to 2 mole of O2. And then we are now in moles of CO2, of O2. And the last step is to change the grams. So we're going to have 1 mole of O2, and that weighs 32.0 grams. So my final answer is 95.8 grams of O2. And you can check your answer. If you look at 24 grams, that's about 2/3, or I'm sorry, 1.5 moles of CH4, and this would require twice as many moles of oxygen, and this would be 3 moles of oxygen, and 3 times the molar mass is 96 grams. All right. I need you to practice that a bit, but there are homework problems to do so. And it is important, and it's pretty straightforward. Let's talk about another way of converting, and this is a term that we're going to hear a lot, or we have heard, our carbon footprints. What does reducing carbon dioxide emissions by 1,000,000 metric tons mean in everyday terms? Well, approximately 4 metric tons of carbon dioxide per person per year are emitted from people's homes. The three main sources of greenhouse gas emissions from homes are electricity use, heating, and garbage, waste. When biochemical, when biological waste, like, just food trash and solid waste goes to the garbage container, repository, often down south of here, off of 71. It gives off a huge amount of methane as it decomposes, which is a very potent greenhouse gas. It's kind of cool. New York City and many other places collect this greenhouse gas and use it again for heating and cooking on the stove. Potent greenhouse gas. Okay, for heating, we burn CH4. Hey, we just saw that reaction. Woohoo! And we know that if with sufficient oxygen, this guy goes to CO2. Another greenhouse gas. Okay. Now, electricity. Electricity, I think I've talked to you about, is that we will get our electricity most likely from coal-burning power plants. And just like every fossil fuel, it makes CO2! Yes, yes it does. And how much does it make? Well, for every kilowatt hour, it makes 7.12 times 10 to the minus fourth metric tons. Okay. Well, how much do we use? The typical household uses 1,000 kilowatt hours per month. So if you multiply these guys together, what would you have? Let's take him away. And we'd have 7.12 times 10 to the minus fourth metric tons, usually written like that, of CO2. And this is per kilowatt hour. 1. And then times 1,000 kilowatt hours per month. So we would have 7 point, we would move this 3, this is times 3, so this would be 0.712 metric tons, make that a little cutie so it looks like a T, of CO2 per month. Okay, transportation, the other place we make CO2, because gasoline comes from crude oil, which is a fossil fuel, which is primarily hydrocarbons, and they make 8.81 times 10 to the minus 3 per gallon. You can figure out how many gallons you use. You can figure out how many vehicles per year, and it does come up to quite a bit of CO2 per person. We have increased our driving miles about 34% in the last 15 years, and the fuel economy of new vehicles has declined significantly because light-duty trucks, SUVs, overtook the sales of passenger cars in 2002. If you want more information, look at this site. It's quite fascinating. Okay. All right, let's just look at some other greenhouse gases. Methane is, remember, she is CH4, the simplest organic species. That's a hydrogen. Methane is 20 times more potent a greenhouse gas than CO2. Why don't we talk about it though? Because it's so short-lived and it is very Uh, it has doubled, but it's much, much less than CO2. CO2's at 400 times, or I guess 200 times what the value of methane is. And the methane that's there dies off and is, I guess, a steady state at about uh, 1.8 parts per million. And it went down for a decade. And so it's not discussed very much. Where does it come from? A lot of people laugh about this, especially people who are not familiar with agriculture. But rice paddies decaying, vegetation decaying, we've talked about that a second ago. The landfills, a lot of methane. Refining, if you look at New Jersey and this around Louisiana, you have the eternal flame where they used to burn off methane, and it was kind of spooky. This gives people a lot of laughs because they, ruminants, people who chew, or animals, yeah, well, maybe people too, but animals that chew grass, uh, cud, ruminants, they put off huge amounts of uh, CH4 by belching flatulence. You can't really put a plug in them. Hard to control. Hard to contain, let's say that. And termites release huge amounts. And there's a half a ton of termites for every human being on Earth. I did not know that. Global warming could strongly increase the release of trapped solid methane. There's a picture in your book about of some solid methane compounds that sit at the bottom of the ocean. And other low levels but potent greenhouse gases, laughing gas, that's this stuff. Ozone, freons. This is the stuff that they used in refrigeration, CFCs, for many years. They're now banned, but they're still used in contained systems, but you don't find them anymore in spray cans.